Hey, okay, welcome here. Where are we? We are week 3, day 3. Oh, this is the halfway point. All right. So, got a smile out of you guys. All right. So, and it's halfway of the second half. And so, this is that time that maybe burnout is beginning to set in. And so, push through. But usually then start of next week, the end of the tunnel becomes in view, and energy levels pick back up. So fight through this week, and we're in the middle of a really hard chapter. I know that. And in fact, that's where I want to begin today. So I wanted to begin to say that my plan was to finish 23. I kind of rushed the inductors at the end, didn't even get a chance to talk about the last section, and I was either going to make a supplement or let you just kind of read it and move on. But then it occurred to me that this is probably not the chapter to rush. Of all the chapters to rush, this is not it. It's a long chapter and it's a hard chapter. And you put those two together, and we've already done, almost 3 hours, about 2.5 hours yesterday. We did something like 80 minutes the day before. And I thought, you know what? Let me just go back and finish this chapter at a reasonable pace with a little more clarity. So this is a way of saying I'm still in 23. I'm going to start here with 23. I'm going to do some more examples from 23. I'm going to spend some time on 23. And I think that will be best. If there's anything to rush at some of the other chapters later on that are easier. And the next chapter is actually one of the shortest chapters. There's only 4 sections in it. So I got to thinking that today I go 4 sections, we'll be done hopefully early, and then I go, this is the perfect opportunity to just take 23. So I'm just going to take 23 kind of slowly, wrap it up, and then start with 24. Hopefully we'll get 24 done, but even if we're not, we're a little behind. And then I just thought, so what? We'll make it up at another time. Or even if we get to the end of the semester and we don't quite make it up, that's kind of normal. So that's just what happens. And so that was my thinking about what should happen here today. So with that in mind, I'm going to come back over here and try to do a little better job and a more complete job with the inductor. And I know it was at the end of the lecture, and it's one of the hardest things to understand. And I was trying to do a comparison with the capacitor, and that's where I'm going to pick up here. So I'm going to say here, let's do this. Let me come back here and draw a RC circuit. And so here's the C, here's the R, here's the V. And so we call this our RC circuit. All right. And then over here, let me put this new symbol, which is our inductor, and call it our RL circuit. And it makes sense here. And so this is the new instrument we're trying to understand. And then hopefully then this will give me time to do the last section here, which is what are some of the usefulnesses of an inductor. And particularly that an inductor and a capacitor together is kind of fun to see. So I was trying to say this. I was trying to say that if you look at the voltage on a capacitor, or for that matter, the charge on a capacitor. When you hook it up, it charges and follows this pattern, where when we derived this a few chapters ago, we said it would look like this. The voltage as a function of time, maybe I'll put a V naught to make it kind of stand out, V naught, resistor R. We said it was this 1 over e to the minus t, and then we had this time constant called RC. And then this gave us a second reason for the usefulness of capacitors, if you remember that. The first reason for the usefulness of capacitors was that they stored energy, and then the second one was that they could be used as a timing device. And today we're going to see a third application when we put it in conjunction with an inductor, and we will have what we'll call a frequency selector, and one that can pick out certain frequencies. Anyways, this, like I said, was my attempt to say, if you kind of remember the physics of why the capacitor did what it did, it was this. If we set this to 6 volts, then Kirchhoff's loop rule says the whole loop has to add up to 0. So from here to here is an increase of 6. Then the capacitor and the resistor must add up to 6. And so if you plotted the voltage of the capacitor and the voltage of the resistor, the two of them together have to add up to 6. And so I was saying, when you first start this, you have no charge on the capacitor, hence no electric field. All right, so no opposition. And that means then the current is pretty strong, and you get then 6 volts 6 volts on the resistor. But the capacitor is in the process of building up a charge, meaning it's in the process of developing an electric field, and that electric field opposes the electric field from the chemicals in the battery trying to make the current go. So a moment later, you might have built up to 1 volt on the capacitor, and because of that, you would then have dropped the amount of current, and because of that, you would have dropped the amount of voltage, and hence you only have 5 on the resistor, and again, notice the two add up to 6. Now, a moment later, this would build up more charge, so the capacitor has even more charge. And let me not go through every step, but they would always add to 6, and the capacitor is building up charge, therefore it's building up oppositions with letting the current flow, therefore you get less current, therefore you get less voltage because of Ohm's law. And so this goes down to a 3, this goes to a 2, this then goes to a 1, and eventually a 0. Oop. 0 on that one, 6 on that one. So eventually, we would say the capacitor has built up to 6 volts. But again, what I wanted to kind of illustrate here was not only this equation, but the physics of how we have an opposition from the current to flow based on the electric field that is developed inside the capacitor. And in this case, the electric field comes from charges. And I want to basically say the same thing again for the inductor. That if you looked at the voltage on the inductor and the voltage on the resistor, again, the same logic would say they have to add up to 6. And again, the same logic would say that there is an opposition. But here's the difference. The opposition from the inductor is an electric field created by a changing magnetic field, a changing magnetic flux. And so these two circuits have a lot the same, kind of in reverse, because this one is saying that you have an opposition because of the one way of making the electric field, but this has an opposition because of the other way. And so I started this chapter saying Faraday's law is going to show us that there is 2 ways to make an electric field. One way of making the electric field is just from charges, and that's what we've done for the last few chapters. But what's new for this chapter is the second way of making an electric field is a bit more complicated, a bit more advanced. We like to say moving magnets make electricity. And so this isn't necessarily a moving magnet, but what you're trying to do is put current through there. And if you put current through there, that makes a magnetic field. And as the current increases, you change the magnetic field. And if you change the magnetic field, you induce an electric opposition. And that's the fundamental principle. So without putting it in equations, just trying to get you guys to understand in concept that an inductor is like a capacitor in the fact that it has an opposition. It opposes the current from flowing. And it does that in a way that is different than the capacitor. The capacitor, like I said, makes the electric field from individual charges. That's the first and simplest way of making an electric field. That's why we studied it first. But this one, this is the hard one. This makes an electric field. This makes an opposition because of the changing magnetic field. And what's interesting is the changing magnetic field comes from the current that's in the inductor itself. And so hence we call it self-induction. And so that's why we started this section saying, hey, let's talk about mutual induction. And really, I said the transformers were mutual induction. So we already kind of covered mutual induction. And I think mutual induction is easier to understand. It's the self-induction. It's when the current within itself opposes itself is where it gets kind of tough. And you'd think it might be easier because you only have one object involved instead of two different coils, but it's because the coil here acts as both the primary and the secondary that it gets harder to understand. So I hope that clarified the physics behind the inductor, and then I'll go ahead and kind of do the same logic. That what would happen is you would first start to connect it and you would say, hey, make the current go rushing in. And your reaction would be, whoa, okay, wait. If you're trying to rush the current in here, that means you're trying to go from no magnetic field to something. And that means there's a significant change to the magnetic field. That means there's a significant induced electric field. That's the Faraday's law. In fact, maybe I'll put that back here on the board here. EMF is equal to negative the number of turns times the derivative of the change in flux. And so when you first connect it up, you are actually going to get a lot of voltage in the inductor. And so this is what I mean when I say the capacitor and the inductor have similarities to them, but they're almost the reverse in their similarities. Because here, when you start with the capacitor, you have no voltage. But here, when you start with the inductor, you get a lot. You don't have any current yet. And so if I were to make a plot of the current versus time, I guess I would say it's starting with 0, a lot like the charge on the capacitor started at 0. However, it's changing quickly. And so let me give it a slope. And so this is where I'm going to have you dig deep into your calculus and kind of remind you that the value of the function could be 0, but the slope could be very big. And the voltage then has to do with not the value of the flux, but the change of the flux. And so it's this slope that matters. Okay, so that's why the inductor will start off with a huge opposition. When you first connect it up, you're going to get this enormous amount of opposition. Or maybe enormous is a little too strong. You're going to get enough that it equals the push from the battery. And because of that, these two balance each other and there is no current. And if there is no current, then there is, IR is the voltage on a resistor, then there is no voltage there. Now, of course, as time goes on, you are going to have current. See, because remember, this graph is saying, yeah, you may have no current at the beginning, but you are gaining current. And so once you get some current, you might say, well, now the voltage on the resistor has built up. And if the voltage has built up to, say, 1 volt, that means there's 5 for the inductor. And of course, if there's 5 for the inductor, that means there must be a voltage of 5. That means there must be an electric field. And remember, that electric field is Faraday's law, so it comes from the changing flux, and the changing flux comes from the current, so you must have a changing current. It's just not at a high rate. And so it changes its slope a little bit. It has less of a rate. That's why we go down from 6 volts to 5 volts. But it still has a slope, and so it's still increasing, and so now the resistor builds up to a higher current. So maybe it's 2 volts, which means that there's 4 for the inductor. Of course, that means 1 lower than 5. That means, of course, it does have some voltage, so that does mean there is some change in flux. That does mean the current is still increasing, but it's not increasing at that same rate. And I hope you kind of get the idea that the current would continue to increase And as the current continues to increase, the voltage on the resistor keeps, sorry, why did I start counting? I got these backwards. So as the current continues to increase, and therefore the voltage on the resistor continues to increase, the voltage on the inductor continues to decrease. And again, since the voltage on the inductor comes from Faraday's law, and it comes from the changing flux, and the flux comes from the current within itself, we must be saying the change of the current is going down. And so this keeps going down and changing its slope. And eventually, as you can see here, we are going to get to a point of 0 voltage on the inductor. And that would simply mean there is no more change in flux. That means we have then a steady current. And so this tapers off to a constant, steady current. And so this pattern that we see for charging up the capacitor is kind of the same pattern we see, and we don't like to use the word charging up because we're not charging the inductor, but we are energizing it. We're giving it current. It is creating a magnetic field, and the magnetic field is getting bigger. Eventually, though, the magnetic field becomes constant, which of course means there's no more changing of the magnetic flux, which means of course there is no more electric field, so there's no more voltage. So eventually the voltage on the inductor goes to 0 when the current reaches its peak, and then the magnetic field reaches its peak, but the electric field goes to 0. So these two fields are going on at the same time, and that's what makes, I think, the inductor, or this whole chapter, kind of the harder thing to do. Well, this is where then I probably rushed that too quickly at the end, so I thought I would restate that and show you an actual connection for this. But I like what your author does, and I'm going to do the same thing. Your author says, look, if you do the Kirchhoff's loop rule here, you can do this. You could say you would get the voltage from the battery minus the voltage from the inductor minus the voltage from the resistor, and if you add them up, you should get 0, right? That's the full loop. And then he says, well, if you think about the math here, the resistor's the easy one, that's Ohm's law. What's this? And this is this. This is Faraday's law. And so you could write this as minus N d phi dt. And so we could dive a little deeper, and I will, but let me just separate it out from the equation, and then we'll come back to this equation. But your author says, okay, so this induced EMF, which is equal to the number of turns times the derivative of the flux. And again, going to the beginning of this chapter, the flux is the magnetic field, the area, times the angle between the two. All right. Well, here's where actually holding an inductor might be useful. So I'm going to come over here and hold this. This will be my inductor. And so literally, physically, this inductor is nothing more than a bunch of wires wrapped around in a coil. It's what we call a solenoid from the last chapter. In fact, this one even says that it has 180 turns. Okay? Now it's 180 turns from the first to the last. You might even see on this one that there are some plugs that are what we call tapped in the middle of them. And so between this one and this one, it's less than 180, and it says it's 1/5 of 180. And then the next one is 1/5, and the next one is 1/5, and the next one's 2/5. Okay, and so we can change the number of loops to whatever we want, and so that would have an effect because this is part of the puzzle and number of loops. Okay. Now let me keep working on this. Let me do 2 steps here. The first one, again, going back to the last chapter, I'm going to say, well, what is the magnetic field? Well, the magnetic field comes from this solenoid. And in the last chapter, your author said that the magnetic field from a solenoid was this mu naught times little n. Actually, let me be careful. I can't remember if he used a little n. I think he did this. I think he called it the turn density. So it's the number of turns divided by the length of the solenoid. And so you might remember near the end we had 3 equations. Maybe I'll put them here where he said that, let me just give them to you because they involve some vector calculus. And I'll put them here on the board. But he said this is the magnetic field you get from a long straight wire. Hopefully that one looks familiar because that's one we used the most. That was the one on the test. All right. This second one, this was the magnetic field at the center of a ring. That was actually on the test too, now that I think about it. It was a multiple choice one on this one. What's the magnetic field at the center of a ring? The one that I don't think was on the homework or on the test was this one here, which was the magnetic field inside a device like this, which you call the solenoid. And that's what I'm going to take advantage of then today, is this one, even though, like I said, we didn't get a chance to talk too much about it, and mostly because I knew we would come back to it on this chapter here. All right, so let me use the one that we haven't used very much and say, okay, this is the magnetic field from something that looks like that. And those are the 3 that you were asked to think about. And like I said, we've done these 2 quite a bit and haven't yet done this one. So we're going to do it now. Yeah.
I just want to make sure I understand this correctly. So I remember you, for some of the homework policy you would go over, you talked about how for some of the calculus you could understand things like a chocolate bar.
Oh.
You were to the little fragment of
Right,
it.
right.
What would stop you from understanding, since that's a cylinder, from using the middle equation to find a fraction of the cylinder?
Oh, okay. So so you guys online can be sure. You're saying this is a solenoid, and then this is a single loop,
Yeah.
and they almost look the same. So now let me see what your question is. Shouldn't these equations be the same? I think, is that what you're getting at? No.
I'm just wondering why it would be incorrect for you to use the middle equation if you were to understand, if you were to take a fraction of the cylinder.
Oh, okay. I guess the answer would be, if I have just one loop, okay, I would do this, and this would be it right at its center. Okay. But what will change is between one loop and a solenoid is, you could imagine then I have a second solenoid right here and another one right here. Okay, now the sum of all of these contribute to that field. However, each of these is further away from this point. So it wouldn't be as simple as just say take this and multiply by the number of loops.
Oh, okay, so for that one you could just multiply.
Right, right. Yeah, I think I understand your question now a little bit better. You're thinking, why don't I just take this one and then multiply by the number of loops? But the problem with that is this loop way over here doesn't contribute that amount. That's the field it makes at its center, but how much field does this one way over here make over here is a different question. So yeah, so it wouldn't be, I like your thinking though, very good thinking. I would attempt, you would have said just multiply that by the number of turns and you would get a solenoid. But because they're at different locations, each ring contributes less and less.
Okay.
And that's when you include that factor, that each ring contributes less and less, you get that equation.
Okay. Thank you.
Okay, good, yeah. All right, so coming back here then, and giving us a chance to do a little mathematics here. And it might look like we're making things hard, but believe me, we're going to make them easier here in just a second. They get harder at first. Maybe it's like cleaning the garage. You know, you walk out there, and at first you just pull everything out of the garage, and it's all over the driveway. And you're like, oh man, you're just making things worse. Okay, but I'm going to restack them and put them back, and so hopefully things will be better at the end, but in the middle, they're looking messy. All right, so I'll say it again. This is the magnetic field. I'll just leave this alone. This is the A. This is the area. That would be the area of this where the flux goes, and so it would be the circular area of this solenoid here. Here's one that we probably need to mention, because again, it does require us to go back to the last chapter and his picture where he said, okay, so this is the equation for the solenoid. That's true. So that's why I put it here. But the direction, and that's how we got that right-hand rule. We focused our attention more on the single loop, but if the current was going, like this, we said, okay, the flux would go that way. And if you put a ring right next to it, it would still go that way. And right next to it, it would still go that way. And so even though this ring moving out contributes less, at least it's always in the same direction. When what I'm trying to get out of that then is what your author says here for a solenoid is the magnetic field goes through that opening. And then, of course, if you take a cross-sectional area, normal to it is also in that same direction. So the field and the area vector are in the same direction. So cosine of 0 is just 1. So that's one thing that makes this easier. Now, here I get to our main point, is if you look at this solenoid, which we're now going to call an inductor, you will see that there are, of course, two ends, so I'll square that. There's a mu naught, there's an area, there's a length to the solenoid, and the only thing changing is the current. And this is why I said we're going to make this easier. Here's what I'm going to do. Is I'm going to take this voltage right here, that is from Faraday's law, and I'm going to replace it with this statement. V naught minus, and I'm going to group all of these together and just call it L. The inductance of this inductor. Okay? And so really, and so this is why I said we're going to kind of simplify our thinking. Instead of thinking that the EMF comes from the change in the flux, and that's really what's happening, it's the change in the flux. But the thing that's making the flux change is the current. So we can just put everything else in one group and say it's related to the change in current. And so what that means then is this L, which is the inductance for this type of device, a solenoid, would be equal to n squared mu naught times the area over the length. And so for this particular section, we can say Faraday's law is simplified because Faraday's law says you get an EMF if you change the flux. And I'll say it again, I've been saying it this whole chapter. How can you change the flux? Well, you can change the flux by changing either the magnetic field, and there's a lot of ways to change the magnetic field, or you can change it by the area, and we saw that with the motion EMF, or you can change the orientation, and we saw that with the generator. But for this case, and in a case when we're dealing with a circuit, the only way to change the flux is by changing the current. So it makes sense to talk about the voltage, and so I'll just say, let's talk about the voltage in an inductor as being proportional to how the current changes. And so I might call this inductance a special case of Faraday's law. And I know this is a long chapter, but I'll go all the way back to 2 days ago when we started this one. I said, one thing neat about this chapter is it's all based on Faraday's law. I mean, we could just say, hey, there's an induced EMF from Faraday's law and everything else just falls into place. We're done. Physics is about knowing how a few powerful fundamental concepts explain a universal phenomenon. But then we need to look at all those individual cases. And so we looked at the motional EMF. We looked at mutual inductance, including the transformer. We looked at the generators. But now we're looking at Faraday's law as it would produce an induced voltage on itself. And the only way the flux can change is from the current. So we might as well put all the other factors that have to do with flux, like area, length, and number of turns, and we might as well put that in one big group, and don't even think about those being separate anymore. Just say that is some value based on, we call this geometry, right? The number of turns, the area, the length, and just put it in one big step and call it L. Because again, an inductor makes a back EMF, an induced voltage. And it does that because the flux changes. But the only way to change the flux in something like this is to change its current. And so that's why I wanted to spend a long time on this little step. And your author did too. Okay, so that in mind, we should probably then pause for a moment and say, all right, now when we talk about inductors, we will say an inductor has a certain amount of inductance. Now, if you wanted to dive deeper into the physics of why an inductor has its inductance, you could begin to see why. It has to do with the flux when it creates a current. And so we could talk about how long it is, we could talk about its area, we could talk about its number of turns, but if we just ignore all of the individual factors that make up the inductance, we can just say it has an inductance. All right, and so that's what I want to say. And so what would the units be for an inductor? Well, maybe you can kind of see it if you move this to the other side. You would have, and I guess I want to do square brackets here to say what are the units. But it would be a volt in the numerator. And when you bring this over to here, you would have an amp per second. Now, granted, that's a compound fraction and I can simplify it, but I'm not going to. Just like when we did accelerations last semester, it was nice to talk about the units in meters per second each second. Could you simplify it? Sure, and we did. We often wrote it as meters per second squared, but it was nice to talk about it conceptually that an acceleration meant you change your speed by 1 meter per second each second. Another good example is the unit for the magnetic field, a Tesla. We said it is the amount of force you get if you had one charge moving at 1 meter per second. So again, it's a compound fraction, and we could simplify it. We did the same thing with resistance. Resistance was a volt over an amp, which is a coulomb per second. So maybe that's a bad example because that's not a compound fraction. But it is a ratio, and that's what I want to get at right here is what's the meaning of this. In the past chapters, I said if you wanted to understand what 10 ohms meant, 10 ohms, if you had a resistor of 10 ohms, what that is saying is you have to apply 10 volts to it in order to make 1 amp flow through it. And so what I'm trying to say here is if I have an inductance of 10, what I mean by that is it would induce a voltage of 10 volts when you had a current of 1 amp per second changing. And so an inductance of 10 produces 10 volts when the current is changing at a rate of 1 amp per second. An inductance of 100 would mean you get 100 volts when the current is changing at 1 amp per second. And like we do with a lot of these units, we give it a name in honor of the great scientists working in that field. So these are referred to as Henrys. And so more than any time ever, I've been saying this, you're seeing a lot of new units. You've seen Faradays, you've seen ohms, you've seen amps, you've seen volts, and now you're seeing Henrys. Okay? And Tesla is another tough one. All right. And so all of these are built on each other, and so we will say that an inductor has a certain amount of Henrys. And in fact, I want to use this one a little bit later, so I'm going to come over here and measure it and write it on the board. And you guys, at least you in class people, well, both of you in class and online, will remember that when we did the lab on capacitance, we had this meter. And I said, turn it on and turn it to the part that says LCR. And LCR, the L part was for measuring inductance. The C was for capacitance and R is for resistance. So now you can see that we've got these nice little meters and little dials divided into thirds so we can measure our electronics. We can measure capacitance, we can measure inductance, we can measure resistance. All right, so this one is still set on capacitance, probably not a surprise. It looks like it's on the 200 nanofarads or picofarads. That's what we did last time in the lab here. But I'm just going to take this, and instead of trying to calculate it, I mean, I guess I could try. I could get the number of turns, I could get the area, I could get the length. I'm just going to take my meter here and hook it up. And let me put my dial. I have a feeling it's somewhere in the range of millihenries. So I'm going to put my meter on a maximum of 200 millihenries. And it didn't like that. Let's try. Okay. Okay, I'm going to take what it says, but you can see I'm pausing here. What?
Your fingers?
Oh, well, the wires are all insulated, so I don't think my fingers matter. Okay. All right, so, oh, okay, now it looks good. No, I'm still in micro. Okay. Well, I'm going to go with this. See where it leads me. If I get into trouble, we'll see what happens here. All right. But this says about 135. and it's microhenries. So I'm going to put here 135 microhenries. Okay, and so let's okay. Well, we'll test its value in a minute, but I'm questioning a little bit. All right, so let me just put that up there. But I wanted to point out, notice it's in henries. That's the big thing I wanted you to see at this point. All right, now, with that in mind, and here's where I'm going to say, let's not take the actual time to solve this mathematical equation. We kind of did the same thing with the capacitor, but can you see that this is just an equation involving current now, and we can solve it for current? Now, it's a hard equation, right, because it's got a derivative. In fact, maybe I'll kind of set the stage to set it, or to solve it. I guess what we could do is we could put V naught minus IR, and then L di dt. But I think for us it will suffice to say, let's just get to the results. Let's not solve this like we did when we did the capacitor. It's really the same thing. Let's just get to the result so we can actually start doing some calculation. But if you wanted to solve this, you could divide both sides by L. You could, actually let me not do that. No. Let me leave the L here. Let me divide both sides by V naught minus IR di dt. Then let me bring the t over to here. dt equals to L V naught minus IR di. And so you've heard me say this before, these last semester and this semester. This is a differential equation. Fortunately, it's what we call a separable differential equation. And so we could integrate it. We could say that you connect it, so you start at time 0, and then you ask the current is 0. When you start. And so I'll say, okay, I'm integrating the current, so starting with 0 current, starting at 0 time. And then a little bit later, call it time t, we would now get to a current of I. Now, here's where I'll skip the same math we did for the capacitors. You can kind of see, isn't this a natural log? 1 over I? Trying to solve for I. So this will be a natural log, and then we'll take the limits of the natural log, then we'll exponentiate it. And if we did all that, we would come up with the current is equal to, and we would get this V over R, 1 minus E to the minus T, and we would get this L over R. Yeah. And this was my way of saying, I even probably talked too much about it already. Let's not actually do the mathematics, but let's get to the result. And so what we would have is an equation that looks a lot like the equation we had for the charging capacitor. So now we have an equation for the energizing inductor. Because we're not charging up, we're not putting any charges on the inductor, but we are building up its current. And in a moment we're going to see that is actually giving it energy. And so we like to say this is energizing the capacitor. And this is the part that I rushed at the end, and I said, so an inductor would build up and get a current, and your author right here does all this math that I was talking about. There it is, the inductance of the solenoid, and eventually comes up with this equation right here, and maybe I'll make it a little bigger. But there it is. Some maximum current, which will be V over R, and then 1 minus e to the minus tau, and tau is the time constant. And so an inductor can also be used as a timing device. And so one thing we can say about an inductor, like a capacitor, we could use it as a timing device. And so we talked about using a capacitor, and they're just so much easier, so we usually do. But an inductor can work just as well as a nice little timing device. And it's why then I tried to show you this circuit, and maybe did it a little too fast, so I thought I'd come back here and say, let's take a look here at an inductor in a circuit here. Now, just so you can kind of see what's going on here, let me take my inductor and say, okay, here's what I'm going to do. And as you guys have seen me do in the lab many times, I said, okay, let's hook up your measuring device at the end. Let me get these out of the way. Those are for later. But I'm going to take my 6-volt power supply, and as we tried to write in the diagram, we're going to say, okay, plug in this 6 volts to the inductor. Then from the inductor, we'll go to the resistor. And so this is my resistor. And I've got a bunch of them. They're actually inside this box. There's a bunch of long wires in there, and I can turn the dials to make it as long as I want. I've got it set here at, looks like 100 ohms. I think yesterday I had it at 1,000 ohms, but I'm going to go with 100 here. And then it returns back. And so I claim, if all this makes sense to you, that when I touch these together, when I close the switch, current's going to try to rush through there. And at first the current will be 0, but it'll build up, build up, build up, and it'll make that shape that's, well, you saw me draw. And so I did this kind of quick, and it wasn't actually a very good looking signal. So I thought, well, I'll try it again, but it also let me vary a couple things to hopefully give you a deeper understanding. And so I'll mention this measuring device again, starting with the idea that the vertical axis is going to then measure the voltage, or how much current I have on my resistor. The horizontal axis is going to measure the time. And because I changed the resistance, I also changed the time factor. I think I was on 100 nanoseconds last time, so this is 1 microsecond per division. All right, but hopefully, if I get this all set up, when I connect these together, oops. Oh, that's kind of ugly. Let me try my trigger level. No, trigger level looks pretty good here. Ah, there we go. The little metal pieces bounce. It's kind of hard to get a good contact, so I do it a couple of times. But my point is, we do see the current follow that mathematical shape. And then just to show you, let me save this one. So I'm going to go reference and then save it. Okay, so I'm going to leave that one on the screen, but I'm going to change the inductance. Remember, this is saying that the time constant, the rate at which it builds up, is based upon the inductance and the resistance. So I'm going to change the inductance. And so remember, we said this is the inductor, right? It's the number of turns. And so if I were to take this and maybe put it right here, now it says instead of having 180, I have 2/5 of 180. Okay? My point is, I have less inductance. Less inductance would mean I have a smaller time constant. A smaller time constant means the current will build up faster. And so hopefully I will still see the current build up, but it'll do something like this. And build up at a faster rate. So let me go back to channel 1 and get it all ready. Okay, so I'll leave the saved one up there so we can compare them. And so now when I have a lower inductance, and there I get a little faster rate. So hopefully that will help you understand this a little deeper, and now probably I should show you a problem or two, because I will say understanding the inductance and why there is an opposition and all this math is kind of hard. Fortunately for you guys, I want to say actually doing the problems hopefully is pretty straightforward, because now we have the equations done for us. And so hopefully all this kind of gave you the background, so when you read the question you know what parameters go in the equation. All right, so I wrote down that this would be good to try number 57 and 69 here. All right, so let me try and switch over here to the book. And I think it was around page 1054 were the problems. Yeah. All right, and 50, ooh, did I say 59? No. What'd I say? 57. Yeah. Am I in the problems? Problems and exercises, yeah. All right, so 57 here says the 4 amp current is flowing through a 7.50 millihenry inductor and is switched off in 8.33 milliseconds. What is the induced EMF? All right, so this is kind of the reverse of what I was saying here. Let's see. I don't want to erase that. I want to talk about this on the next problem. Why don't I leave these here and come over to here? But what this one is getting at is saying, here's how we're going to talk about the voltage in the inductor. I'll use this as an opportunity to say the fundamental physics part of this is the EMF equals minus the number of turns times the change in flux. But when we apply that to this special case of an inductor, we can change that to the voltage of an inductor is minus L di dt. And then, knowing a little more mathematics with calculus versus algebra, we could say, well, the average, and so I'll borrow a symbol from your math class and put a bar over it. So the average voltage would then be minus L times the change in current over the change in time. So in other words, instead of taking a microscopic limit, I can just do kind of a bigger picture of time. And that's the way your author phrases this. So he's saying, hey, let's take it from calculus just to algebra, which kind of makes sense because this book is based only on algebra. And so it's not until we get to the university one that the calculus kind of kicks in here. And so what they're saying here, that you're going to switch it off. So they just told you that the current's going to go from 4 to 0. So that's the change in current, from 4 amps down to 0. And they tell you the time it takes, and they tell you the inductance, and so they're asking for the EMF. So this is just kind of plug those in and see what you get. So, all right, my voltage would be negative. Now I forget how much inductance we had in 57. 7.50 milli. So 7.50 millihenries. So that's how much inductance I have. The change in currents, well, let me go final minus initial. So the final current is 0 amps. The initial current is 4 amps. And all of this took place in a change of time of 8.33 milliseconds. And then fortunately, there's a milli top and bottom, so I won't even need to enter those into my calculator. I'll just drop those off. Also, fortunately, maybe I should put some parentheses here so I can see I've got to subtract it first. But when I subtract this first and I get a negative, that negative with that negative is going to now make a positive. Okay, so it's going to be a positive. Which, let me pause right there. Because again, this brings us all the way back to the beginning of this chapter. Faraday's law says we oppose the change. This inductor is based upon Faraday's law. You're trying to turn off the current. So what is the inductor doing? It's trying to make a voltage that keeps the current going. It always opposes the change. And so not a surprise that this comes out to be a positive. You're trying to turn off the current, and the inductor is going to say, no, I want to keep it the same. And that's our fundamental principle of Faraday's law. All right, so as I put these two in here, so this minus and this minus make a plus, I'll grab my calculator here and do the numbers first. Then let's talk about the units here. But this is 7.5 times a 4 divided by an 8.33. And so this is going to produce about 3.60 volts. Oh, and I should talk about the units. Does it come out to be volts? It should, right? That's our unit analysis. This is an equation that says we're asked for how many volts or how much potential, so the EMF, so it should come out in units of volts. And so here we have our henries. And remember, a henry then is a volt per amp each second. Okay, so there's my henry. And of course, this right here is an amp. And I think I'll just write it here as amp per second, kind of in the numerator, like that. So you can kind of see, oh yeah, that makes sense. The amp per seconds are going to cancel off, and you're going to get your volts. So 3.6 volts is how much this inductor would do, at least at first. So if you walked up to it and turned it off, this is its average according to this math. So it might be higher than that at first and then taper off. But in either case, this has a lot of interesting consequences for the electrical engineer, because you could say a lot of things about this that, it doesn't want to shut off, which could be good. Many of your computers have a small little inductor or capacitor or both like this, because inevitably there's always that flicker of power, right? There's always that surge of power. You've ever been in your room studying, or the lights, and you just see them kind of flash. There's that momentary brief. And computers don't really respond well when the current goes down. So by having an inductor built into that and it's plugged in, then all of a sudden during that little flash, it can get its current momentarily and its voltage momentarily from that. And so this is a way to keep the power on, and your computer is unaffected by that flash. I notice mine, that my power at home, when it does flash, if it's a short flash, my computer's fine. But sometimes the flashes are a little longer, and then the computer just goes blah. Then it goes through a whole reboot cycle, and it takes a while, and it's got, to kind of recapture everything. And so fortunately, they're also built so that if the flash is too long, the loss of power is too long, you can still recover. All right, well, let's try the other example. All right, so that was number 57. Let me try number 69. And so 69 says, if you want the characteristics RL time constant to be 1 second, and you have a 500 ohm resistor, what value of the self-inductance is needed? Okay, so again, want to emphasize, this is pretty hard stuff, but the end result is we're going to give you some pretty, hopefully, straightforward questions that say just plug and chug, okay? But you got to know where to plug and chug it. So that's why we wanted to make sure we went through all these details. That's why I took extra time here today. I'm going to take half the lecture to just finish this one up. All right, so the time constant is right here. And so the time constant tau equals L over R. And so they give us the R and they give us the time. We're supposed to get the inductance needed. So if you want a characteristic to be 1 second, in other words, a good example of this was just what I was saying with the computer. If you wanted the computer to remain energized during a flash of power for 1 second, all right, how much of an inductor should you put in the device in order to make that last? And that's really what this is coming down to. So I'm going to put here for the time constant 1 second. And then for the resistor, what I read here, 500 ohms. And so we have a 500 ohm resistor. Now the numbers are pretty easy, but the units might take a moment here. And so 500 times 1, of course, is just 500. And then, of course, if you multiply it by an ohm and a second, you get that. However, let me remind you of what an ohm is. An ohm is the amount of volts you would get per amp. And then let me do what we usually don't do in a math, which we convert a simple fraction into a compound fraction. But let me do that so you can see it. So this is going to be 500 volts, and then I'm going to move this second into the denominator of the denominator. And so now I have my compound fraction, and so there it is. There's our henries. And so this is going to be 500 henries. And so that's the size of inductor I would need in order to have my computer last for a whole 1 second, which, by the way, is a long time and a big inductor. So this is not normal operations of a standard computer. It can be other computers. Years ago, before I was teaching and I worked in aerospace, we had this giant computer system that could actually run for 15 seconds. And of course, we had a room about the size of this room loaded with capacitors and inductors to keep it running for 15 seconds. And the 15 seconds was good because in the room next door was a giant diesel generator. And so if the power went out, it automatically started the generator, and we figured the generator would take 5 seconds to get running and little space just in case. We tripled that, and we said, all right, we need to have enough computers and inductors to keep the computer system running for 15 seconds versus, again, and when you're running a giant aerospace company, if you lost power in the middle of a work day, you could lose all that data from people's work. This could be millions of dollars in one day, and so it is totally worth putting aside a whole room that can run a computer for 15 seconds and a diesel generator that can start within 15 seconds. It was just smart business practice to make sure you can do that. And so some of this data information, and the world's a little different now too, very different now too in terms of storing energy. But anyways, that would be the answer to it. Now there's one more thing, and again, probably too much on this inductor here, but I probably should say one more thing. I keep talking about the inductors being energized, and there is a set of energy here. It might be seen in this equation here. Because watch this. What if I multiply both sides of this equation by I? And so if I take the first term and multiply it by I, and I take the second term and multiply it by I, and I take the third term and multiply it by I, you can see something very useful here if you kind of study the math. For example, the first term. That first term, and maybe putting next to it, I should put the circuit. Since we've done so much talking, we've erased the circuit, but here's the voltage supply, here's the inductor, here's the resistor. This is our circuit that this equation was talking about. And so that first equation is the voltage of the battery times the current, and it has a plus sign in it. So if you remember, voltage times current is power. So I would describe this first term as how much energy per second, how much power is being delivered by the battery to the circuit. And then these other two have a negative sign. So I would say then these other two must be the power coming away from or being consumed by the circuit. So this is the power being delivered to the circuit. This is the power being consumed. And you might even recognize this, I squared R. Isn't this the power being consumed by that resistor? Ah. And so there's my clue. What must this be? And that must be the power being consumed, or you might even say absorbed into the inductor. And if you remember that power is the rate at which energy changes per time, we could then integrate both sides of this equation with respect to time. Because if you do that on the right-hand side, the times go off and you just have an integral of dE, which is E, the energy. And so this is my last step for this section, saying, okay, how much energy is absorbed by this inductor? And this will allow me to figure that out. This is why I kept saying, as the current builds up, we are energizing the inductor. Now, the other side of the equation, fortunately, the dTs also cancel off, and I have a very easy integral to do. I can factor out the L, and then I just have I dI, which, if you remember, the integral of x dx is just x squared over 2. So this is going to become I squared over 2. And so here is the last step of this pretty advanced discussion on electronics. And that is the energy stored in an inductor is dependent on how much current. And that kind of makes sense. Isn't the current dependent on how much magnetic field you get? And so you're really saying here that an inductor is also an energy device. And so hopefully you're seeing that these inductors are a lot like our capacitors. You could use either one to store up the energy. And that's what I was telling you the story a little while ago when I was working in aerospace. That, look, you can use this to run the computer for a while. In our case, we were shooting for 15 seconds. There's energy stored there, whether it's a capacitor or inductor. It's nice to have both. I would say the difference, though, is that the capacitor is storing the energy in the electric field, whereas the inductor is storing it in the magnetic field. But they both can store the energy. And so this is an equation that I think you'll need for one of the homework problems there is, how much energy does this inductor have here? All right, well, now that I did those two examples, and let's see, and I did the transformers yesterday here, let's finish off this really long chapter and say, all right, let's look at 23 sections 11 and 12 kind of as a group here. And we're still going to talk about these inductors, but now you're going to see a third usefulness. I say third again because I would say both the inductors and the capacitors can be used to store energy. Both the inductors and the capacitors can be used as a timing device. And something quite fun happens when you use the two together and you have an AC circuit. And so your author says, let's introduce you to a concept of reactance. Let's build an L, an R, and a C circuit. And let's hook it to an alternating voltage or an alternating current source. All right, so it's been a while since we've seen this symbol, we saw this when we were dealing with the power in the, I want to say it's chapter 20, but it could have been 21. I think it was into 20. But we said, what if you put an AC signal, and in this case, let me hook it so that the capacitor, the inductor, and the resistor are all in series. And so notice here that the current, I, would try to flow through, and I say try because there's going to be some opposition. This was a whole discussion for the last hour. Isn't it going to be hard for the current to flow through because? And do you see all three reasons? One of them is the resistance of the resistor. That's the easiest one to understand. That was our chapter 20, Ohm's law. Resistance is, as the name implies, it opposes the current from flowing. Okay. But what I hope I tried to get across in the last hour is you could think of this capacitor as having some opposition to flowing also. Because what's going to happen is it's going to start to build up charges on it. And when it builds up these charges, it will then have an electric field, which will be in opposition. Now, it's a kind of a different opposition. So let's not call it resistance. Let's give it a new name. And here it is. Let's call it reactance. The capacitor opposes current for a slightly different reason than the resistor. It opposes it because of an electric field that builds up. Now, the electric field builds up because the charge builds up. And so I'm going to say that there is a certain amount of opposition because of the capacitor. And that's why the word is called reactance. Okay? Now, let's look at the inductor. We just, again, spent a long time on the inductor saying, look, the inductor has the same idea. It opposes the current because it has an electric field. Now, its electric field is a little different than the capacitor. In fact, both of these are good devices to show at the same time because I said, and I'll repeat again, there's two ways to create an electric field. The first way was at the beginning of this semester, chapter 18. We said charges make an electric field. But what we're learning in this chapter is there's a second way of making an electric field, and that is a changing magnetic field. And this gets its changing magnetic field from its own self, its own current. And to make it even more interesting, the current is constantly changing. And so unlike the last problem we just did, that we would only see the effect when we connect it, this we're going to always see the effect because it's an AC source. And so we're going to have the current go one way and then switch it. And then another way and then switch it. Another way and switch it. We're going to keep switching it back and forth. And so this inductor is going to constantly going, okay, I need to make voltage, 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 voltage. And so it's always going to make an opposition. And again, I'll say it makes an opposition different than the resistor. It makes it from an electric field. So let's call it a reactance also. So in other words, we're going to say that the capacitor and the inductor oppose current not because of resistance, but because of their own internal electric field. And we'll just refer to that as its reactance. So, I would say that this device right here, this current that's trying to flow in this very interesting, and I would even say reasonably complex circuit, this RLC circuit, there is an opposition to the current flowing because of resistance, reactance, and reactance. Now, you might even say it's kind of a different reactance in the sense that this reactance, which comes from an electric field, And that electric field comes from charges. Whereas this reactance is also an electric field, but that electric field comes from the changing magnetic flux. But either way, it's still a reactance. Oh, let me give you then the final word here, impedance. Impedance then is the total combination of what is opposing the current. And I would say what is opposing the current is a reactance from the inductor, a reactance from the capacitor, and a resistance from the resistor. And again, we like to separate the resistance from the reactance, but overall, together, collectively, we call that the impedance. The impedance is the overall result of this circuit. How much current am I going to get? And the symbol we're going to use here is Z for the impedance. And to give you kind of a similarity of Ohm's law, let me come over here to the side and say, look, before we got into this more complicated stuff with capacitors and inductors, we had the simple case of Ohm's law. We just said the amount of current would depend on two factors. The numerator is the push, how much voltage, and the denominator is the amount of resistance. We're going to do the same thing. We're going to say that the amount of current is V, the amount of push, divided by the amount of opposition. And the opposition is not just resistance, it's also reactance, and so the collectively of the two together is called impedance. And so this section starts off with, I'd say, a lot of vocabulary. Just, okay, here we have a bunch of words that say, all right, why are you opposing the current? So I'll say it again. We're opposing the current for these three devices. This device is opposing it just from its resistance. This device is opposing it because of the electric field that is made from the charges. This one is opposing it because of the electric field that's made because of Faraday's law. And so you might say those are three different pieces. And they're right, they behave differently. And that's really what this circuit is about. This is the beauty of this circuit. Because let's talk now. What if the frequency is low? What if the frequency is high? All right, so I'll start with low. Low would basically mean that you are not changing the current very quickly. Now remember Faraday's law. Faraday's law says the EMF is related to the change in flux. So I would say at a low frequency, this inductor just doesn't do much. Remember, it's Faraday's law. Faraday's law says, and maybe I'll put it over here again, the voltage on the inductor is equal to minus L di dt. See, it's related to how quickly that current is changing. So I would say from the inductor's point of view, this is boring. The inductor's really not doing anything. The inductor, you might say, is making a small voltage, but maybe even negligible. And you'll say, at low frequencies, this just doesn't stop it. Okay. And maybe that's good and bad. I would say if you're trying to get current through there, low frequencies would go through this inductor really well. But here's the problem. What about this guy? this guy is a capacitor. So remember, the voltage on a capacitor is the charge divided by its capacitance. And if you're at a low frequency, what you're really saying is you're giving time for the capacitor to build up a charge. And so what ends up happening is when you first change from negative to positive, the charges go in here. They're not really stopped by the inductor. The inductor says, fine, you're not changing very quick. That means I don't change my flux very quick. That means I don't make a very strong back EMF. That means go through. I don't produce much voltage. But here, it starts to build up charge, and then this can actually have the time to build up a lot of charge and therefore build up a lot of an electric field and then oppose this. So I would say that at low frequencies, this guy is stopping the current. And so you're not going to get much current through this at low frequencies. In fact, that's why I thought it might be good to actually kind of hook this up, kind of maybe see it in action. And so I took an AC source right here. And so in my AC source, let me set it to kind of a high frequency here for a moment. I'm at 56,000. Now, let me, as you guys have seen me many times say, let me disconnect my measuring device. That'll be the last thing to hook up. Okay. Let me hook up my circuit. So I have this, and somewhere over here, I have my capacitor board. You might remember working with these. I'm just going to pick this smaller one down here. All right, so I'm going to feed it into a capacitor. And let me not make the whole circuit yet. Let me just make the capacitor and the resistor. Okay, so I'm going to complete the circuit. Okay, so if I got this right, it goes into the capacitor, goes into the resistor, and goes back, and I've completed my circuit. And so I'm going to use this fancy scope again to say, let's measure how much current gets through here. And so I will just do that by looking at the resistor. Okay, so how much current goes through here. Now, so you can see it, I'll switch it over to the display. I'll also have to change the mode setting on this, and I probably need to clear off all of these. Okay. All right. And so right now, I am measuring this sinusoidal pattern, goes up and down. You can see my time scale is at 10 microseconds. I'm not going to worry too much about how big it is or how long it is. I just want you to see that it goes up and down. I also want you to see that if I change this knob here, I can change the frequency. See how it's higher frequencies? And see how it is lower frequencies. Okay? Maybe I'll make one adjustment here. But watch what happens when I get to low frequencies. I'm at 51 right now. Lower, 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 lower. Nothing much interesting. Do you see how the peak went down right there? And so remember what I'm measuring here. I am measuring how much current there is. And what I'm trying to show you here is that if I am at a low frequency and I'm hooked to a capacitor, the capacitor is going to give me a lot of opposition. It's going to give me a lot of reactance when the frequency is low, because that means it has time to charge up. And that's when it gets an electric field. So at these low frequencies, I'll even go to lower frequencies. Whoops, wrong way. Lower, 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 lower. See how it gets less and less? But see how the reverse is true. If I go to high frequencies, high frequency, high frequency, high frequency, high frequency, and about there, it doesn't matter how high I go, it lets about the same amount through. Because at this point, the capacitor, you put a little on, and then you take it off. You put a little on, you take it off. You put a little on, you take it off. It never has time to build up a charge. And so what we like to say here, conceptually here, is a capacitor lets The high frequencies go through, but it opposes the low. Now, let's think about the inductor. The inductor is exactly the opposite. The inductor, right here, is from Faraday's law. Remember, Faraday's law says the voltage is related to the rate of change. How quickly does it change? And so what that would tell me is that at high frequencies, or as I just said, the capacitor doesn't have much opposition, the inductor does. And I'll show that before we maybe go on our break here and finish this up when we come back from our break. But let me replace this capacitor with an inductor. And I'll do a different inductor. This one is essentially like this one. It just has more inductance, because remember, part of the inductance is the area and the number of turns. This actually has more turns. There's 200 wires wrapped around here. That's only a little more than the 180, but it's got a lot bigger area. So there's quite a bit of inductance. So I want to look at this one. And so let me just disconnect my capacitor. I'll put that over here. And I will replace with my inductor, and then I'll change frequencies. And I might be at too high of a frequency. Let me try this range here for a second. See if I can, yeah, good. See that variation? And so I'm going to start at a low frequency. So this is 4.76 kilohertz. But watch what happens as I go to higher and higher and higher frequencies. See how the amount of current goes down and down and down. And so, without getting into the math yet, just want you to understand how these two things are functioning. This one functions based on Coulomb's law, but this one functions based upon Faraday's law, and Faraday's law says the opposition is based upon the rate of change. And so an inductor at high frequencies would stop it. And it's a good time to take our break, but when we come back from our break, now we can get to the grand finale, which, what's the purpose of this? This is a velocity selector, frequency selector, right? This thing will block the high frequencies. That's what the inductor's job is to do. The inductor's job says, I'm not going to let high frequencies come into this circuit. What is the capacitor going to do? The capacitor is going to say, I'm not going to let low frequencies come to this circuit. The end result is a compromise in between and says only at a particular and narrow range will frequencies be able to go through this. And hence, I can now use this as a tuning device. I could select whatever radio channel I want. A combination of an inductor and a capacitor. I could go, oh, I'm going to listen to K-Earth 101. And 101 means that that frequency coming in is 101 megahertz. And if I took this apart, I would find an inductor and a capacitor inside of it, and they would be set just right so that things higher than 101 get blocked by the inductor, frequencies lower than 101 get blocked by the capacitor, and the only thing I hear at one moment is K-Earth 101. But if I get tired of that, I can switch to another radio station. So I could go, well, I'll go to KLOS, which is 95.5. So I change the dial here, and I change what frequency to come through. but I only get one at a time. I use a combination of this LCR circuit. All right, well, like I said, lots to talk about. Let's take our break, our 15-minute break. Let's come back at 10 till, and let's put some numbers in here and call it a wrap to this chapter and get started with the next one. All right, hey, okay, well, welcome back here. Let's finish this up, and we really need to get started now on the next chapter. But like I said, this stuff can get pretty complicated and pretty deep. And so I'll say it again, that hopefully, if this is a little fuzzy to you, the end result is really what you need. So we've got these equations. You're going to read the problems, plug it in. You have to understand enough to know what equation to grab for and what each variable in the equation means, but perhaps you don't need to know it as a deep of level as I just kind of conceptually explained it. Which is why then, let's finish this off with the math and say, all right, let's put some math into this. I kind of got started right here in the math by saying there is a analogy of figuring out how much current by taking the voltage and dividing it by this thing called the impedance. The impedance being the total effect of both the reactance, the two reactants, one from the inductor, one from the capacitor, and the effect of the resistor. And so your author does these individually. He says, what if you were looking at the reactance of an inductor? So he says X sub L. And this is what he calls is the reactance of our inductor. And before the break, I'll just go back and say, what is the reactance of our inductor? I was trying to say that because of Faraday's law, the higher the frequency, the more the reactant, right? Faraday's law says the induced EMF is proportional to the rate of change. And so there is a factor of F. That's the biggest one. The other ones that he doesn't derive and isn't so obvious is it's 2 pi times F. That's whole, one cycle. We've got an AC circuit, so that's not a surprise. And also, hopefully not too much of a surprise, is the value of that inductor. What is its inductance? And so this is what your author says. If you only had an inductor by itself, you could say that the current would be the voltage divided by the reactance of the inductor. So that's what I'll put maybe in one block right here and say, okay, that would be the effect if you only had the inductor by itself. And again, notice what the math is saying, that for high frequencies, you get very little current. And so, again, in terms of selecting a frequency, the inductor lets the low frequencies go through, blocks the high frequency. It has a very high back EMF for those very high frequencies. Now, on the other hand, for a capacitor, your author says, let's use the symbol X, okay, and he calls this then the reactance. Again, like we've been saying, but it would be the reactance of the capacitor. And he says it's kind of the same, but in reverse. And that's what I've been trying to say for this last hour about the inductor and the capacitor. There's a lot of similarities between them in reverse. So in other words, the capacitor would have a big reactance if the frequency was low. This was what I was saying before the break, that you would have time for the charge to build up. This would be Coulomb's law, and being opposite of Faraday's law, or the reverse of Faraday's law. And so what you would get here is saying that the reactance is low if you're at a low frequency, but at high frequencies, the reactance is small. And so again, if you only had a capacitor by itself, you might describe the current this way, as it being the voltage then divided by its reactance. And so again, just studying these, you'll see that the inductor blocks high frequencies, the capacitor blocks low frequencies. And this is what I was saying is the magical piece of this circuit, is it can then narrow in on a balance between the two and select just one frequency. So to finish the math here, let me get rid of those equations and say your author, again without proof, says that the total opposition, that's the impedance, of a full circuit that would have an inductor, a capacitor, and a resistor, so it has all three of them, then must be made up of all three of these. It must be having an opposition because of the reactance of the capacitor, it must be having an opposition because of the reactance of the inductor, and it must be having an opposition, and I just erased it, but hopefully it was obvious, that it from the resistance of the resistor. However, they aren't simply just added together. I wish it was that simple. If it was that simple, well, we'd probably take the time to go through the math. Your author says it actually comes out to be, and it's kind of related to Pythagorean's theorem, and so we have to combine them in, the fancy word is quadrature. In other words, what we say is the total opposition to letting current flow depends on what? And you can see this term right here. This is a balancing effect between the two. And so this is why they subtract them, because I keep saying both of these are doing kind of the same thing in reverse. And so the total effect of the two of them is the difference between them. And so that's where this term comes from. And then, of course, the other effect is the resistance. And so we got resistance and reactance combined together to give us impedance. And maybe a little surprising, because we didn't go through the math, is that they're combined using Pythagorean's theorem. And so the best thing I can say is, let's just settle on the math and call it Pythagorean's theorem and say this is what we need to solve the problem. So what we need to solve the problem to figure out how much current is we need to go V divided by the impedance, and the impedance would depend upon the resistor, the inductor, the capacitor, and the frequency we're at. Because remember, both of these depend on frequency. Now, here is really kind of the grand finale of this circuit. Remember I told you then, we call this circuit a frequency selector. It's called an LCR series circuit, and it selects the frequency, and you can kind of see when would you get the most current. Well, looking at what I will call the equivalent of Ohm's law, wouldn't you get the most current when the impedance is the lowest? All right, so let's come over to the impedance. When would you get the smallest impedance? Now let me be careful with that, because I'm going to say if I hook up a given resistor and a given inductor and a given capacitor, so I can't change those, but I can change the frequency. That's the key. The only thing that changes with frequency are these two. This one doesn't change. But I would say then you get the most current when XL equals XC. And so this is what our math is saying. Our math is saying that when these two balance each other, you will get this number right here equal to 0. And so you would just have the square root of R squared. And so your most current would be V divided by just R when you're at the appropriate frequency. And that's what I wanted to show you and finish up. Say, well, what would that appropriate frequency be? In other words, this circuit is designed for what frequency? Well, it's a balance between the inductor and the capacitor. It's when these two are equal, and that's these two equations. So let's run through the math. So when 2 pi f times L equals 1 over 2 pi f times C, when those two are equal, that's the magical frequency. And so if you put over here 2 pi squared f squared LC equals 1, and you go to solve this for frequency, you're going to get 1 over 2 pi squared LC. If you take the square root, you're going to get 2 pi times the square root of L and a C. And so this circuit, like I said, is designed for a particular frequency. Too high, it's blocked by the inductor. Too low, it's blocked by the capacitor. Just right is what it's tuned for. We'll put in some numbers and do an example, but let's hook this up here. Well, we've had all this stuff. I've been showing you the capacitor. I've been showing you the inductor. Let me actually hook up that circuit. So as I was telling you in lab and going to show you again, I like to say, let's use the measuring device and disconnect it first and hook it up last. Let's hook up the circuit. So here's my AC source. I'm going to take advantage of the fact that it's already going right to my inductor. And then I'm going to, as the picture shows, feed it to my capacitor. Then feed it from my capacitor to my resistor. Then feed it from my resistor back to my AC source. So I would say I have just built these four things: the AC source, then to the inductor, then to the capacitor, then to the resistor. And now I want to see how much current goes through there. So what I will do is use this little fancy device that measures really voltage, not so much current, but I'll just measure the voltage on the resistor, which would mean it's measuring current. And so let me just play with the knob here a little bit. And do you see, right? It goes off the screen here, so maybe I'll change the scale. Maybe I'll move it up a little bit. But without looking at any numbers right now, the size of this is the amount of current. And so if I go to a high frequency, higher, 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 see how it's getting less and less current? I would say at this point, I am at a frequency so high that this guy's stopping it, right? That's the reactance, high frequency. But if I lower the frequency, so lower, 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 see how I get more and more, lower, 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 more, 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 more. Oh, but if I even go to lower frequencies, less, less, less. And so what I'm saying here is once I start getting to these lower frequencies, this one starts blocking it. And so there's this magical point where this is tuned in for just the right frequency. And I think I can find it here. I'll just go look here until it's the biggest. And maybe I need to change scale, it gets so big. All right, so right, see right there? Okay. So lower frequencies, so that's too low. Now I'll go to high frequencies. High frequencies, looks like it peaks right there, and then when I go to higher frequency, I get less. And so I would say the magical frequency is right there. And according to this, I'm at 3.9 kilohertz. And so to finish this section off, let me try my math here. This math says that the magical frequency would be this calculation. I need to know the value of my inductor and the value of my capacitance. So let me measure them and write them down here. All right, so let's see. Where's my meter again? Okay, so as we started here, I can take my meter. Let me do the inductor. So I'll disconnect the inductor. I'll hook it up. This one should be bigger than the one we measured earlier today. So it's probably somewhere in the millihenries. So this says 16.3 millihenries. I better write that down so I don't forget. And so this L is 16.3 millihenries. Let's try the capacitance. Now, the capacitance is right here. And as you guys seen on the lab, it says it's 0.1 microfarads, but that just means it's close to that. So let's give this a try. Let me take my capacitance meter. Let me plug it in. Let me switch the dial over to something that I'll go to the nanoscale. So 0.1 micro should be about 100 nano. And it's pretty close, 96.9. So 96.9 nanofarads. And so now let me grab my calculator and see what my calculator says the magical frequency should be now that I just measured it. And so like a lot of times we do in a lab, hey, let's calculate it, let's measure it. If they don't match, let's figure out what we did wrong. Okay, so here I have the L, so 16.3 times 10 to the minus 3, okay, times 96.9 times 10 to the negative 9, okay, enter. Let me take the square root of all of that, all right, then multiply by a 2, okay, multiply by a pi, hit enter, and finally last step, let me take the reciprocal of all that, and this says I should get a frequency of 4004 hertz. And I would say we were very close to that when we took our measurement. We were 3.94 for our measured magical frequency. All right, well, so I'm glad it worked out well and worked out right. So let me just say, let's do 2 more examples and move on to the next and much shorter and less difficult chapter. But our last chapter also on magnetism, and so it is still a little bit on magnetism and both the interaction of magnetism and electricity. All right, so that's why we call it electricity and magnetism. So I thought another good example to do is number 100. And so let me jump back over to the book and scroll down to number 100. And it simply says this. The lowest frequency on an FM radio band is 88 megahertz. A. What inductance is needed to produce this resonant frequency? So that's the fancy word for this magical frequency I've been talking about. It's resonant frequency. What does it naturally want to respond to? It naturally wants to respond to the balance between the inductor and the capacitor. All right. So what inductance is needed to produce a resonant frequency if it is connected to a 2.5 picofarad capacitor? So I would say that is this equation right here, where the frequency, the resonant frequency or the magical frequency is LC. And so I thought this would be a good one, not just to do the problem, but also then to say what I was mentioning right before the break, was that, see, this is how this thing is designed. This is designed to pick up a particular frequency. And if you look on this old radio, it even says FM radio, and it gives numbers. It goes from 88 to 108. And if you even look closer, it says megahertz. And so what it's saying here is you put up the antenna, you hold it out, it is designed to capture all these different frequencies that are coming from all these radio stations, but the first thing it does is goes through this antenna, and it goes through one of these LCR circuits, a frequency selector, and only one of those can get through based upon the value of my capacitor and my inductor. You might even remember, and I grabbed them again to bring them out, what I do with those variable capacitors, here they are, is when we had capacitors and I passed them around, I said, here is a set of plates that you can then vary the area overlap and hence vary the capacitance. And I said these were then useful because we took this one out of an old shortwave radio and this one out of an old ham radio. And so again, you can turn the dial and change the capacitance and then change whatever frequency you're trying to select. And of course, you're only going to do one at a time. And so you're listening, in this case, we're on the lower end of the FM scale. So we're at 88 megahertz is the design here. So keeping that in mind, I would come over here and say, all right, if I want to get 88 megahertz, what is the value on combination of my inductance and my capacitance? And in this case, they give me one of them and I've got to find the other. And so I would again say probably the hard part of this chapter is not so much the math. Once you know the right equation, it's to understand really what they're asking. You know, so I've just done all the hard math getting to the equation. Even then I skipped a lot of the math. I just say, okay, now what does it all mean? Hopefully so that you can then go, So if you ever read this question on a homework or a test, you'll go, oh, this isn't a hard math one, but it is hard to decide what equation am I supposed to use. And it's this one. You need to know by reading the question that it is a resonant frequency and you're looking for this magical frequency. All right, so I got to come back here and read it. The lowest frequency on an FM radio band is 88 megahertz. What inductor is needed to produce this resonant frequency with a 2.5 picofarad capacitor? So coming over here, I'm looking for the L, the inductance. They gave me the picofarad for its capacitance. And so maybe the thing to do first is to get rid of that square root. Well, now maybe move the 2 pi over here and then get rid of it. So I'll do that. So let me take my 88 mega and multiply it by a 2 and a pi. And then I will just hit square. So this comes out to be 3.06 times 10 to the 17. And then, of course, now that I squared it and moved the 2 pi over, I would be left with just an L and a 2.5 times 10 to the minus 12. So now, if I move the L over to here, and then this number to here, I would be saying take that number and multiply it by 2.5 times 10 to the negative 12. And now I will take its reciprocal, and we are looking at 1.31 times 10 to the minus 6 henries, or 1.31 micro henries. Which, by the way, if you remember the start of class, I got out the meter and measured 135 microhenries for this one here. And so if the tuning on this capacitor, or the tuning circuit on here had a capacitor of 2.5, then it would need an inductor of this type. And this doesn't fit real well, so it's probably something a little different than that. But it would need some kind of appropriate inductance. Now, watch what happens when I continue on here. It says B, the capacitor is a variable capacitor, all right? So again, you can see why this is on a radio. You've got a little knob sticking out here and you just tune it. And you turn it to whatever capacitor you want. And as you change it, you are now selecting a different magical frequency, a different resonant frequency. So it says the capacitor is variable to allow for the resonant frequency to be adjusted as high as 108 megahertz. So remember I said the value on an FM radio dial is from 88 to 108 megahertz. Okay. What must be the capacity then, the capacitor at this high frequency? So again, kind of the same thing, that we would say I'm trying to pinpoint 108 megahertz. And like I said, usually the inductor doesn't change. So the inductor is just a bunch of wrapped coils inside of my electronic box. So this is the 1.31 times 10 to the negative 6 henries. And now we're looking for the new capacitance. Okay? And since we're trying to get a higher frequency and the capacitance is in the denominator, I should be looking at a lower capacitance. So in other words, if I was tuning this position right here with the most overlap would be the highest capacitance. This would be the dial setting at 88 megahertz. And as I tune it this way, I'd get less and less, and I would go to those tuning of those higher and higher frequencies here. And so grabbing my calculator here, I'm going to go 108 mega times a 2 times a pi. So that's this number. And then I'm going to square it. So I will just have, well, I'll write this down. Once I square it, 4.60 times 10 to the 17th. And then now 2 pi, and I've squared it. This would be 1.31 times 10 to the minus 6c. Let me move this over to here. So times 1.31 times 10 to the negative 6. And so that's, now I'm left with 1 over c. So let me take the reciprocal of that. And I am at 1.66 times 10 to the minus 12 farads for the capacitance. And that's picofarad. So just like I conceptually said, I would expect to turn the dial so there's less area overlap, so there's less capacitance as I try to tune it to this higher and higher frequency. And so that's the purpose of that one. Now let me try the other one right below it. It's number 101. Same idea. It says you have an LRC series circuit that has a 2.5 ohm resistor, a 100 microhenry inductor, and an 80 microfarad capacitor. Find the circuit's impedance, and notice this, it's important, find the impedance at 120 hertz. Because as we're talking about here, we have impedance, and that depends upon all three of them, the inductor, the resistor, and the capacitor, but the reactance of the inductor and the capacitor each depend on the frequency. Now my suggestion when I do these problems is kind of do it in piecemeal. I'll leave this equation here, but I like to find what is the reactance of each of them individually, each the inductor and the capacitor. So I like to just start off and say XL equals. And so it's 2 pi f times L, and XC equals 1 over 2 pi FC. And let me just get a number. Let me work with those separately instead of try to put them in one big giant equation. All right, so if I go 2 times pi times the frequency of 120, and then times, let me do the inductor, 100 micro. I'm looking at 0.0754 ohms. So not much there, although that's a relative term, so maybe I need to look at the other ones and see what that come out to be. All right, so let me do the capacitor. So let me go 2 times pi times F, which is 120, and then times the capacitance, which is 80, what was it, microfarads? Okay, so 10 to the minus 6. And so that's the denominator. Let me take the reciprocal of that, and we're looking at a 16.6 ohms. Now, let me also point out here that it doesn't surprise me, as we've just been talking about the physics, we're at a very low frequency, 120. And it was the capacitor that blocked the low frequencies. So the reactance is much higher for the capacitor than the inductor. The inductor uses Faraday's law, and we're just not at a high frequency. Now, the resistor itself is 2.5 ohms. And so as you study these three elements, you can clearly see at this low frequency, the one that's stopping the current really is the capacitor. The resistor's doing a little bit, and the inductor's hardly doing anything. Most of the effort, most of the stopping or the blocking is coming at the capacitor. So this is a frequency that is not the resonant frequency. It's not the magical one. It's lower than the magical one. It's much, much lower. But that's our goal. Find the impedance of this, right? Find the circuit's impedance. So if I find the impedance, I would subtract these two. So let me take the 16.6 and subtract the 0.0754. Let me then square that. Let me add it to the 2.5 squared. Let me hit enter, and then finally taking the square root gives me a total opposition of 16.7 ohms. So again, not a surprise that it's just a hair above 16.6, because again, what's really going on in this circuit is it's being blocked by the capacitor. It's such a low frequency, the capacitor is charging up. As it charges up, it makes an electric field. It stops it from coming in. And that's our physical concept. So this one's just a very, very low frequency. But look at the other one. The other one says find the circuit's impedance at 5 kilohertz, 5.00 kilohertz. So I'm going to do the same thing, and so maybe I'll put here, this was at 120. Let me put at 5 kilohertz. And then I'll do this a little faster, but we're just going to have now a higher frequency. And so 2 times pi times 5,000, and then times the inductance, 100 micro. All right. So now, being at a higher frequency, and remembering inductors operate on Faraday's law, which is equal to the rate of change of the flux, we get more reactance. It's gone up quite a bit. It's gone from, in the hundredths to 3. And of course, hopefully the capacitor has gone down quite a bit. So let me go 2 times pi times 5,000 times the capacitance, which again was 80 micro, and take the reciprocal, and now we're, I guess, on the other extreme. Now we're at such a high frequency, the capacitor's not really stopping it. Although we're not too high, because the inductor's not stopping it as much as before the capacitor was stopping it. So but still clearly not at the magical frequency. Remember, these two are equal at the magical frequency. So we've gone higher than the magical frequency, and that's what this would tell me. Now, to get the impedance, then, this is where we're going to have to add them in quadrature. So I'm going to take the 3.14 minus the 0.398, and I'll square that number. And then I'll take the 2.5 and square that number. I'll add them together. I will then take the square root. And so we're looking at a total of 3.71. And that's then, again, maybe not too much of a surprise. It's a little bit more than the inductor itself, because the inductor is, or the resistor is a significant contribution. It's not quite as close here, but so we're higher than the magical frequency. But and hopefully that's kind of the next question here. C says, if the voltage of the source is 5.60 volts, what is the current at each of these frequencies? Okay. Well, I'm glad he asked that one, but again, that one's kind of a boring one because I've done the hard work. And so now that I've done the impedance, so C, if I wanted to get the current at 120 hertz, I would take the voltage and divide it by the impedance at that frequency. And if I wanted to find the current at the 5,000 hertz, again, I would take the voltage and divide it by that impedance. And so I've done those impedances. So I'll go ahead and put in those voltages. Let's see. So 5.6 divided by, and then again at 120, we're looking at 16.7. And so we are looking at 0.335 amps. Where at the higher 5,000 frequency, I have a much lower impedance, still not the magical one, but definitely lower. So I'll divide it by 3.71. And now, again, a lot more current, but again, still lower than the magical. But we're at 1.5 amps, so we're starting to get a lot of current here. And D, good, I'm glad they asked it. What is this resonant frequency, and what is the current at that one? All right, so let's do D and E. So D then would be saying, okay, so this magical frequency is 1 over 2 pi times the square root of L over C. And based on the numbers I already did, I haven't used this phrase in a while, but if you keep paying attention to reading your math, not just doing the math, but what does this say? You saw when I went from 120 to 5,000 how the resonant frequency must have been in between them, because we resonate when those are equal, and it gets higher, so it went up, and this one would go lower, and it went down, and somewhere they were equal, but we went too far. And so I'm hoping that I get a resonant frequency somewhere less than 5,000, but more than 120. So I'll take the L and the C and multiply them together. Let's see, it was 100 micro and 80 microfarads. So 100 microhenries for the inductor and 80 microfarads for the capacitor. So I'll multiply those two together and then take its square root. Then I will multiply by 2 and also multiply by a pi. And then finally, the last step is I will take the reciprocal And so I multiplied these all out, took the reciprocal, and we are looking at 1,000, I'll call it 780 hertz. So sure enough, less than 5,000 and more than 120. Oh, snag this again. Can you still hear me, Ron? Now, here to me is the big one here is what is the resonant frequency? And so E would be saying take the currents and divide it by the impedance. And I'll say it again, the impedance then is the total of both the resistance and the reactance. So it's a combination of the resistor, the capacitor, which is Coulomb's law, the inductor, which is Faraday's law. But also, remember this, we can save ourselves some work because it was a lot of work in A and B to find the impedance because we had to punch in the frequency. Here we can save ourselves some work because we already know the magical frequency happens when those two are equal. And so those are going to cancel off. And so at the magical frequency, we would just get V over R. And so this is the 5 point, what's the voltage? 5.6, is that what I read? 5.6. And the resistance is the 2.5. So we're going to be a little over 2 amps here. Oops. And so 2 1/4. Well, 2.4 amps. Yay! And so that's the meaning behind all those. So maybe one last time, and we'll kind of quickly demonstrate the next chapter. And like I said, I wanted to do a little more, and I ended up doing a lot more on this chapter. But like I said, hopefully the details of this, because I do think by far we're in hard material and a long chapter.